Look up at the night sky, and you'll see stars, pinpricks of light scattered across the darkness. But what if I told you that's just the surface of a far grander, invisible architecture? Beneath it all lies a vast, mysterious scaffold, a cosmic web of dark energy, stretching across the universe like an unseen hand, shaping everything we know. This isn't science fiction. It's the hidden reality of our cosmos, and today we're diving deep into its 25 most mind-bending mysteries. Picture this: galaxies aren't just floating randomly in space. They're connected by colossal threads of dark matter and energy, forming a sprawling network that defies imagination. These filaments, some stretching hundreds of millions of light years, are the backbone of the universe. And yet, we can't see them directly. Dark energy, the force accelerating the expansion of the cosmos, works in the shadows, pushing galaxies apart faster and faster. It's as if the universe itself is breathing, expanding with a power we can barely comprehend. How does it work? Why does it exist? And what does it mean for the fate of everything? This journey isn't just about distant galaxies or abstract physics. It's about unraveling the very fabric of reality. Dark energy isn't just out there, it's part of the story of us. Every atom, every star, every life owes something to the forces weaving this invisible web. And the deeper we look, the stranger it gets. From ghostly voids where galaxies refuse to form, to the chilling possibility that dark energy could one day tear the universe apart, these mysteries challenge everything we think we know. So buckle up, we're about to explore the edges of understanding, where science meets the sublime, and where each discovery leads to even bigger questions. The cosmic web is calling, and its secrets are waiting. Back in 1998, astronomers made a discovery that sent shockwaves through science, one so bizarre it earned them a Nobel Prize. They found the universe wasn't just expanding. As we'd known for decades, it was doing so at an ever-increasing speed, like a car pressing harder on the gas pedal the farther it travels. This wasn't supposed to happen. Gravity, the glue holding galaxies together, should have been slowing everything down, pulling the cosmos back in on itself over time. Instead, something invisible and unstoppable was overpowering it, a force we now call dark energy. Think of it like a cosmic tug of war. On one side, gravity tries to keep the universe tightly knit. On the other, dark energy relentlessly stretches space itself apart, creating more distance between galaxies with each passing second. And the stranger part: the more the universe expands, the stronger dark energy's grip becomes. It's as if empty space isn't empty at all. It's brimming with this mysterious pressure, pushing everything away from everything else. Einstein himself almost predicted it a century ago. His equations hinted at a cosmological constant, a repulsive force that could balance gravity, though he later dismissed it as his greatest blunder. Turns out he might have been onto something after all. Modern telescopes studying the faint glow of ancient supernova, exploding stars billions of light years away, reveal a universe accelerating faster than any model predicted. Graphs of this expansion don't curve gently, they spike upward like a mountain with no peak in sight. What does it mean for the fate of the cosmos? If dark energy keeps strengthening unchecked, galaxies will eventually vanish over the horizon of visibility, leaving future astronomers with a sky nearly empty of stars. But here's the real kicker: we still don't know what dark energy actually is. Is it woven into the fabric of space-time, a new, undiscovered particle? Or something so alien it rewrites the laws of physics? This isn't just a puzzle, it's the biggest unsolved mystery in modern cosmology, hiding in plain sight, driving the universe apart one invisible push at a time. Einstein called it his greatest blunder, but he might have been right all along. That mysterious lambda term he scribbled into his equations, the cosmological constant, was meant to balance gravity's pull with an equal and opposite push. At the time, he believed the universe was static, unchanging. When Hubble proved it was actually expanding, Einstein tossed the idea aside. Yet today, that very same mathematical placeholder might hold the key to dark energy. Here's where things get weird. Quantum physics tells us empty space isn't truly empty. It's a seething foam of virtual particles popping in and out of existence. This quantum vacuum energy should, in theory, act just like Einstein's lambda, a constant pressure stretching space itself. But when physicists did the math, the numbers were catastrophically wrong. The predicted energy was 10 to the power of 120 times stronger than what we observe. That's a 1 followed by 120 zeros, a discrepancy so enormous it's been called the worst theoretical prediction in the history of science. So why doesn't the universe rip itself apart? Either something's missing in our quantum theories, or dark energy isn't a constant at all. Some researchers suggest it might evolve over time, growing stronger or weaker like a cosmic dial being adjusted. Others propose exotic new fields, similar to the Higgs boson but far more elusive, permeating space with just the right amount of repulsive force. Then there's the radical idea that Einstein's equations themselves need rewriting, that gravity behaves differently on cosmic scales than we've ever imagined. The stakes couldn't be higher. If dark energy is truly constant, the fate of the universe is a cold, lonely expansion until every galaxy vanishes beyond the cosmic horizon. But if it changes, the cosmos could face a far wilder destiny, a sudden collapse, or even a runaway rip that tears atoms apart. Right now, telescopes are hunting for clues in the flicker of ancient supernova and the ghostly imprint of primordial plasma. Every new measurement brings us closer to answering the haunting question: was Einstein's blunder actually a stroke of genius, or is the truth stranger than even he could have dreamed? The most unsettling possibility hidden within dark energy's mystery isn't just expansion, it's annihilation. Imagine a force so relentless that it doesn't just push galaxies apart, but eventually shreds the fabric of reality itself. This is phantom energy, a hypothetical twist on dark energy that grows stronger over time, and it paints a terrifying portrait of cosmic doom, the Big Rip. Here's how it would unfold. Right now, dark energy's repulsive grip is subtle enough to stretch space between galaxy clusters, but not yet strong enough to overpower the gravity holding individual galaxies together. But if dark energy isn't constant, if it's phantom energy, amplifying itself as space expands, then every passing eon would see its power multiply. First, the space between galaxies would stretch faster than light can traverse it, isolating them like islands in an ever-widening ocean. Next, the bonds holding galaxies together would snap. Stars, once held in delicate orbits, would fling into the abyss. Then, the nightmare escalates. Planetary systems would unravel. Planets would be ripped from their suns. Finally, in the last agonizing moments, even atoms would be torn asunder, protons and electrons wrenched apart as spacetime itself fractures under the strain. The numbers are chilling. If phantom energy exists, some models suggest this apocalypse could strike in as little as 22 billion years. On cosmic timescales, that's shockingly soon. For context, Earth's been around for 4.5 billion years. Humanity, a blink in comparison. And yet, this scenario would erase everything, not with fire or ice, but with an inexorable stretching of the void, leaving behind a universe so fragmented that not even light could bridge the gaps. What makes this idea so haunting is that it's not pure speculation. The equations allow it. Observations can't yet rule it out. Telescopes hunting for tiny changes in dark energy's strength might one day find evidence that it's not just persistent but growing, like a shadow deepening with time. The universe's fate hinges on a number we've barely begun to measure, the phantom energy equation of state. If it dips below -1, the countdown to disintegration begins. And here's the twist that bends the mind even further. In a Big Rip scenario, the end wouldn't be some distant event we observe passively. As the rupture approaches, the stretching of space would outpace the very forces that hold us together. In the final moments, every molecule in your body would be pulled apart faster than the speed of light. It's a conclusion so violent it feels ripped from myth, yet it's lurking in the math, a silent specter in the data. The universe might not just fade away, it might scream. Here's a cosmic riddle that keeps physicists awake at night. Why is dark energy taking over the universe now? Not 1 billion years ago, not 1 trillion years in the future, but this precise moment in cosmic history, when humans happen to be around to notice it. It's called the coincidence problem, and it's one of the most baffling timing quirks in all of science. Rewind the universe's clock to just after the Big Bang, and dark energy was practically irrelevant, a whisper against the roar of radiation and matter. For billions of years, gravity ruled, pulling gas into galaxies and weaving the cosmic web we see today. But around 5 billion years ago, something flipped. Dark energy's subtle push began to outmuscle gravity's pull, and the expansion of space started accelerating. The timing feels oddly convenient. If dark energy had dominated earlier, galaxies might never have formed. If it kicked in later, we might not have noticed its effects yet. So why this Goldilocks moment? Not too soon, not too late, but just when conscious life emerges to ponder it. The numbers make this even weirder. Today, dark energy makes up about 68% of the universe's energy budget, with matter, both normal and dark, accounting for the rest. But scale that back to the universe's infancy, and dark energy was less than 1 part in 10 to the power of 120. That's like comparing the weight of a single atom to the mass of the entire observable cosmos. The changeover didn't just happen gradually, it was a staggering power shift, like a pebble suddenly outweighing a planet. Some theorists argue this isn't a coincidence at all, that dark energy's rise is tied to the conditions needed for life, a concept inspired by the anthropic principle. Others propose radical physics. Maybe dark energy isn't a constant but a field that interacts with matter, its strength waxing and waning with cosmic evolution. There's even the eerie possibility that we're witnessing a phase transition, like water freezing into ice where the universe's vacuum energy is settling into a new state with consequences we can't yet predict. Every measurement deepens the intrigue. When astronomers study baryon acoustic oscillations, the faint echoes of sound waves frozen in the distribution of galaxies, they're essentially taking the universe's pulse across billions of years. Each data point narrows the window on when and how dark energy seized control. Yet the why now question lingers, a reminder that the cosmos might be more finely tuned or more mysterious than we ever imagined. What if dark energy doesn't exist at all? That's the bold claim of a small but passionate group of physicists who argue we've been misreading the universe's expansion entirely. Instead of invoking an invisible, unexplained force, they propose something even more radical, that gravity itself operates differently on cosmic scales than we've ever imagined. This isn't just tweaking the rules, it's rewriting them. At the heart of this rebellion is modified Newtonian dynamics. Born in the early 1980s, MND was originally crafted to solve a different cosmic puzzle: why stars at the edges of galaxies rotate faster than Newton's laws predict. According to classical physics, outer stars should move slower, like planets farther from the sun. Yet observations show they whip around at nearly the same speed as inner stars, as if gripped by an unseen hand. Mainstream science calls this hand dark matter. MND answer: gravity doesn't fade as quickly over vast distances as Newton or Einstein thought. Now, some researchers are stretching MND logic to cosmic scales, suggesting that what we call dark energy might just be gravity's misbehavior in an expanding universe. Imagine a rubber band that stiffens the more you stretch it. Modified gravity theories propose something similar, that as space expands, the gravitational glue between galaxies weakens in unexpected ways, mimicking the effects of dark energy without requiring its existence. But here's where the theories hit turbulence. While Mond elegantly explains galaxy rotations, it struggles with larger cosmic phenomena. The bullet cluster, a cosmic collision where visible matter and gravitational effects visibly separate, presents a glaring challenge. Mond can't easily account for this disconnect without some form of invisible mass, effectively reinventing the dark matter it sought to replace. And when it comes to the universe's accelerating expansion, modified gravity models often resort to elaborate tweaks that critics argue are just as ad hoc as dark energy. The debate cuts to the core of how science confronts the unknown. When faced with a mystery, do we invent new substances, dark matter, dark energy, or do we question the laws we thought were fundamental? Right now, the scales tip toward dark energy, thanks to precise measurements of the cosmic microwave background and supernova data. But the allure of modified gravity persists, a reminder that sometimes the most profound discoveries begin with a simple, heretical thought. What if we've been wrong all along? For now, the universe keeps its secrets. Every telescope trained on galaxy rotations or distant supernova is probing this very question, not just mapping the cosmos, but testing the laws that govern it. Whether dark energy or modified gravity prevails, one thing's certain: the answer will rewrite physics itself. What if dark energy isn't static? What if it's alive? Not alive in the biological sense, but pulsing, shifting, evolving across cosmic time. This is quintessence, a theory that turns dark energy from a passive background force into something far more dynamic. Unlike the rigid cosmological constant, quintessence suggests dark energy could be a scalar field, a kind of cosmic weather system stretching across the universe, its pressure ebbing and flowing with expansion. Picture a vast, invisible ocean filling the cosmos. In some eras, its currents might surge, accelerating the universe's expansion with violent intensity. In others, they could calm, allowing gravity to briefly regain dominance. This isn't just poetic imagery, it's mathematics. Scalar fields like quintessence appear everywhere in physics, from the Higgs field giving particles mass to the inflationary field that supposedly jump-started the Big Bang. But quintessence would be something stranger, a field that isn't frozen in place after inflation but lingers, adapting, shaping the cosmos in real time. The implications are staggering. If true, quintessence could solve the "why now" coincidence problem. Perhaps the field's strength naturally crescendos around this epoch, explaining why dark energy dominates precisely as life emerges. It might also dodge the vacuum energy catastrophe, replacing that absurdly large theoretical prediction with a flexible, evolving value. Some models even allow for quintessence to eventually dissipate, offering an alternative to the Big Rip's grim finale. Yet the theory walks a tightrope of fine-tuning. Why would this field's fluctuations align so perfectly with observed expansion rates? Critics argue it risks replacing one mystery with another, trading a simple, if unexplained, constant for an elaborate ballet of adjustable parameters. Supporters counter that nature loves complexity. After all, no one expected the universe's expansion to accelerate at all before 1998. The hunt for evidence is on. Astronomers scrutinize subtle variations in supernova brightness curves, seeking hints that dark energy's push has changed over billions of years. Others analyze baryon acoustic oscillations, fossilized sound waves from the early universe, for patterns that static dark energy can't explain. So far, the data leans toward a constant, but margins of error leave room for surprises. Quintessence remains a tantalizing what if, a reminder that the cosmos might not just be expanding but breathing. Take the Boötes void, a colossal, nearly empty region of space spanning 330 million light-years, so vast that if our Milky Way sat at its center, we wouldn't have known other galaxies existed until the 1960s. This isn't just an absence of stars, it's a staggering desert where matter is almost entirely missing, and the rules of cosmic expansion might bend in bizarre ways. What if these voids aren't just passive gaps, but active players in the dark energy puzzle? Some scientists suggest they could be warping our measurements of the universe's acceleration, creating an illusion of dark energy where none exists. Here's how the trick might work. When light travels through a void, it doesn't just pass through empty space, it navigates a landscape where gravity's pull is weaker than in galaxy-rich regions. According to general relativity, this should cause photons to gain a tiny burst of energy as they exit the void, like a car coasting downhill. But on cosmic scales, that subtle boost could mimic the signature of an expanding universe. Stack enough voids together, and the cumulative effect might look indistinguishable from dark energy's relentless push. It's a cosmic sleight of hand where emptiness itself masquerades as acceleration. The math gets even stranger when you consider how voids evolve. Unlike dense clusters which grow slower as gravity fights expansion, voids expand faster. Their emptiness begets more emptiness. Over billions of years, they stretch spacetime from within, creating a feedback loop that could amplify their apparent influence. Maps of the Boötes void reveal this in action. Galaxies near its edges are being gently pulled outward, not by dark energy, but by the void's own gravitational deficit. It's as if the universe has sinkholes, and we're misreading their tug as a global force. Yet the void hypothesis has cracks. For one, the sheer scale of fine-tuning required is staggering. Voids would need to be arranged in a precise, universe-wide pattern to mimic dark energy's uniform effect. Worse, recent surveys like the Sloan Digital Sky Survey show that while voids are abundant, their distribution doesn't fully match the acceleration signal. The cosmic microwave background, the afterglow of the Big Bang, also bears fingerprints of dark energy that voids can't easily explain. Still, the idea lingers because it forces us to question what we're really measuring. Every time astronomers calibrate their telescopes to track supernova or baryon acoustic oscillations, they're assuming a universe where matter is evenly smeared, an assumption voids violently disrupt. Maybe dark energy isn't a force but a shadow cast by the universe's emptiest corners. Or maybe these voids are just another piece of a puzzle we're still learning to read. Either way, they remind us that in cosmology, sometimes nothing is just as important as something. Stare at a map of the cosmic microwave background, the afterglow of the Big Bang, and you'll notice something odd. Amid the faint swirls of temperature variations, there are regions chillingly colder than they should be. These aren't random glitches. One particular cold spot, spanning nearly 1 billion light-years, defies standard cosmological models so dramatically that some researchers wonder if it's a fingerprint of dark energy's hidden structure. The cosmic microwave background is usually a uniform sea of microwaves, cooling to just 2.7 degrees above absolute zero as the universe expands. But the Planck satellite's ultra-precise measurements revealed tiny fluctuations, hotter and colder patches reflecting the infant universe's density variations. Most fit neatly into inflation theory, the idea that the cosmos underwent explosive growth moments after the Big Bang. But that infamous cold spot, it's an outlier. Statistically, it shouldn't exist. The odds of such a pronounced chill appearing by chance are less than 1 in 50. Cosmology's version of a cosmic roll of loaded dice. Here's where dark energy enters the mystery. If dark energy isn't perfectly uniform, if it clumps or varies in strength across space, it could warp the cosmic microwave background in ways that mimic these cold spots. Imagine dark energy as a cosmic tide, ebbing and flowing through the void. In regions where it weakens slightly, space might expand a fraction slower, leaving behind a faint cold imprint in the microwave background. That cold spot could be a shadow cast by dark energy's invisible hand, a place where the universe's acceleration stuttered for a moment, or it could be something even stranger. Some theorists suggest the cold spot is evidence of a collision with another universe, a bubble beyond our own brushing against spacetime and leaving a bruise in the cosmic microwave background. Others propose it's a vast supervoid, a desert of galaxies so enormous that light passing through loses energy, creating a cold illusion. But supervoids this large are nearly as improbable as the cold spot itself, deepening the enigma. The Planck data doesn't settle the debate, it sharpens it. Every new temperature map narrows the possibilities, yet the cold spot lingers, a quiet challenge to our understanding. If dark energy is involved, it means the force driving the universe apart isn't just a smooth, unchanging backdrop. It has texture, structure, maybe even currents we've yet to fathom. And that changes everything. A uniform dark energy fits neatly into Einstein's cosmological constant. A patchy, evolving one, that's uncharted territory where the rules of physics might bend in ways we're only beginning to glimpse. So the cold spot isn't just a curiosity. It's a potential window into dark energy's true nature, a clue that the cosmos might be far lumpier, far more dynamic than we ever imagined. As future telescopes like the Euclid Space Observatory peer deeper into these anomalies, they're not just mapping the universe's past, they're hunting for the invisible architecture of its future. One of the most baffling conflicts in modern cosmology isn't happening in deep space, it's unfolding in the pages of scientific journals. Astronomers call it the Hubble tension, two precise methods of measuring the universe's expansion rate, each backed by mountains of data, stubbornly refuse to agree. One approach studies nearby supernova and Cepheid variable stars, acting as cosmic yardsticks. The other analyzes the faint glow of the cosmic microwave background, the universe's baby picture. Both methods are meticulous, both have been refined for decades, yet they give results that differ by roughly 10%, a gap far larger than measurement errors can explain. At the heart of this discrepancy is a number called the Hubble constant, which tells us how fast the universe is expanding today. The local measurements peering at relatively close galaxies suggest a faster expansion rate, around 73 kilometers per second per megaparsec. But the early universe approach, using the Planck satellite's cosmic microwave background data, points to a slower 67. That might sound like a minor quibble, but in cosmology, it's a screaming red flag. Imagine two clocks, both impeccably crafted, one ticking noticeably faster than the other. Either someone made a mistake we haven't caught yet, or there's a fundamental flaw in how we understand time itself. Enter dark energy. Could this mysterious force be evolving over time, subtly shifting its strength in ways that throw off our measurements? If dark energy isn't perfectly constant, if it was slightly weaker in the past and has grown stronger more recently, it might reconcile the conflicting Hubble values. A changing dark energy would tweak the expansion history of the universe, making early and late measurements align differently than our models predict. It's like realizing the car's gas pedal wasn't just pressed harder over time. It was sticky with an uneven acceleration that earlier calculations didn't account for. But the plot thickens, alternative explanations abound. Some physicists suggest we might be living in a local bubble of space slightly less dense than the rest of the cosmos, skewing our nearby measurements. Others propose undiscovered particles like a new type of neutrino altering the early universe's energy balance. Then there's the radical possibility that our understanding of gravity itself breaks down on cosmic scales, requiring a rewrite of Einstein's relativity. The stakes are enormous. If the Hubble tension holds, it wouldn't just tweak our models, it could crack them open, revealing entirely new physics hiding in plain sight. Every new observation, from the James Webb Space Telescope's sharp-eyed surveys to next-generation cosmic microwave experiments, is a chance to resolve the conflict or deepen the mystery. One thing's certain, in the vast, shimmering tapestry of the cosmos, dark energy might not be the only invisible thread pulling the universe apart. We just haven't found the others yet. String theory whispers of hidden realms, dimensions curled so tightly we'd never notice them, folded into the fabric of reality like origami tucked between atoms. But what if these unseen layers aren't just mathematical abstractions? What if they're the key to dark energy's deepest secret? Imagine our universe as a three-dimensional island floating in a higher dimensional ocean, a brain in string theory parlance, while gravity, unlike other forces, isn't confined to our island. It leaks, and that leakage could rewrite everything we thought we knew about cosmic expansion. This is the brainworld hypothesis, a scenario where dark energy isn't some exotic substance but a shadow cast by gravity's escape into extra dimensions. Picture a sponge soaking up water. The more space expands, the more gravity seeps away, leaving behind an apparent repulsive force we misinterpret as dark energy. It's not that galaxies are being pushed apart, it's that the glue holding them together is quietly draining into the cosmic plumbing. Some models suggest this could explain why dark energy's strength is so bafflingly small, a fraction of what quantum physics predicts because most of its effect isn't happening in our dimensions at all. String theory's extra dimensions aren't just idle speculation. They emerge as mathematical necessities to make the equations work, often visualized as Calabi-Yau manifolds complex, six-dimensional shapes smaller than a proton. But in brainworld scenarios, at least one of these dimensions could be far larger, a hidden corridor where gravity's influence diffuses. Astronomers have even looked for fingerprints of this in the slight weakening of gravity at very large scales, though so far no smoking gun. Yet the implications ripple further. If gravity leaks, colliding brains could trigger cyclical universes, endless cosmic resets where big bangs happen not once but over and over. Dark energy's acceleration might then be a prelude to the next collision, a cosmic inhale before the next exhale of creation. Or perhaps we're witnessing the slow unraveling of our brain's tension, like a stretched rubber sheet finally going slack. Critics argue this trades one mystery for another, replacing dark energy with unproven dimensions. But supporters counter that it solves multiple puzzles at once: the unnatural fine-tuning of dark energy's strength, the Hubble tension's stubborn discrepancies, even the universe's eerie flatness. Right now, the best evidence might lie in gravitational waves, ripples in spacetime that could carry traces of higher dimensions if they vibrate in just the right way. Future detectors like the Laser Interferometer Space Antenna might catch these whispers from beyond our dimensional shore, so dark energy could be more than a force. It might be a message, a cosmic SOS broadcast from realms we can't see, hinting that the universe isn't just expanding, but breathing in dimensions we've yet to imagine. Black holes, cosmic titans that devour light and warp time, are often seen as eternal, but in a universe ruled by dark energy, even their reign might meet a bizarre end. Picture a black hole floating in the void billions of years from now, as galaxies vanish over the cosmic horizon. With no new matter to consume, it would slowly leak energy via Hawking radiation, a quantum quirk that makes black holes evaporate over unimaginable timescales. For a typical stellar mass black hole, this process would take longer than the current age of the universe. But here's the twist: dark energy could accelerate their demise or trap them in a fate worse than death. Hawking radiation hinges on a peculiar quantum effect near a black hole's event horizon, where particle-antiparticle pairs flicker in and out of existence. Normally, one particle falls in while the other escapes, stealing a tiny bit of the black hole's mass. In a static universe, this drip feed of decay would take trillions of years. But dark energy's exponential expansion could stretch space so violently that it severs the delicate quantum threads driving this process. The black hole might be left stranded, unable to shed mass as the universe around it thins into nothingness. Or consider the opposite scenario: phantom energy, that extreme flavor of dark energy, might speed up Hawking radiation. If dark energy's repulsive force grows strong enough to rip apart spacetime itself, it could fracture black holes from the outside in, tearing their event horizons apart like tissue paper. Simulations of these competing outcomes paint a surreal picture. In some models, supermassive black holes outlast all stars, glowing faintly as they evaporate over googolls of years. In others, they're frozen mid-decay, locked in a cosmic limbo as the last structures in an otherwise empty universe. The chilling takeaway: dark energy doesn't just determine how the universe expands, it rewrites the expiration date of everything within it. Black holes, once thought invincible, might face oblivion twice, first as prisoners of an accelerating cosmos, then as ephemeral sparks fading into the dark. Vacuum isn't empty. That's the unsettling truth quantum physics forces us to confront. At the smallest scales, space crackles with energy, particles and antiparticles flickering into existence for mere instants before annihilating each other again. This quantum foam, as physicists call it, isn't some abstract concept. It's real enough to measure, with tangible effects like the Casimir force, where two metal plates placed micrometers apart in a vacuum feel an invisible push as quantum fluctuations outside them overwhelm those between them. This zero-point energy, the lowest possible energy state of a quantum system, should theoretically be the prime suspect for dark energy's origin. After all, if empty space contains energy, shouldn't it produce the repulsive force accelerating cosmic expansion? The math seems straightforward. Einstein's equations treat vacuum energy identically to the cosmological constant, but here's where the theory unravels spectacularly. When physicists calculate the predicted energy density of the quantum vacuum, they get a number 10 to the power of 120 times larger than what we observe. That's not just wrong, it's arguably the worst mismatch between theory and observation in the history of science. Imagine the quantum vacuum as an ocean, its surface constantly churned by unimaginably violent waves. Each wave represents a particle-antiparticle pair born from the void. According to quantum field theory, these virtual particles borrow energy from nothingness, existing just long enough to obey Heisenberg's uncertainty principle before vanishing again. The problem: if you sum up all that borrowed energy across the entire universe, you'd expect space itself to be bursting with repulsive force, enough to tear atoms apart instantly. Yet reality shows only a faint whisper of that power, just enough to nudge galaxies apart over billions of years. This discrepancy has spawned two camps. One argues we're missing something fundamental, that unknown physics cancels out most vacuum energy, leaving behind the tiny fraction we call dark energy. Some suggest supersymmetry, a theoretical framework where every particle has a partner, could balance the books. Others propose a yet undiscovered filter mechanism in quantum gravity. The second camp makes a bolder claim. Maybe vacuum energy doesn't gravitate at all. Perhaps the quantum foam's furious activity simply doesn't couple to gravity the way normal matter does, a loophole Einstein never anticipated. Experiments might settle the debate. Ultra-precise measurements of atomic energy levels could reveal subtle footprints of changing vacuum energy. Others hunt for variations in fundamental constants over cosmic time, a signature that dark energy stems from a dynamic quantum field rather than static vacuum properties. Until then, we're left staring at the quantum abyss, realizing the universe's greatest acceleration might spring from the very fabric of nothingness itself, or something far stranger we've yet to imagine. What makes this mystery so profound isn't just the math. It's the dawning realization that our two most successful theories, quantum mechanics for the tiny, general relativity for the vast, might both be correct yet fundamentally incompatible when it comes to the vacuum. Dark energy isn't merely a force, it's a screaming paradox at the heart of reality, demanding we either find new physics or reconsider what nothing truly means. The cosmic microwave background should be the ultimate blueprint of randomness, a near-perfect snapshot of the infant universe, its temperature variations scattered like paint splatter across the sky. But when scientists mapped it with unprecedented precision, they stumbled upon something unsettling. the universe seems to have a secret alignment, a ghostly axis where these fluctuations follow an eerie pattern. Dubbed the axis of evil by a researcher half-jokingly invoking dark forces, this anomaly suggests the cosmos isn't as uniform as we thought, throwing dark energy's assumed homogeneity into question. Look at the polarized sky maps from missions like Planck and WMAP, and the oddity jumps out. Temperature fluctuations aren't entirely random. Instead, they're subtly organized along a particular direction, as if the universe itself tilted slightly in its cradle. This isn't just a statistical fluke. The alignment spans vast swaths of the sky, with odds of occurring by chance estimated at less than 1 in 1,000. The implications are staggering. If dark energy truly permeates space evenly, how could it allow such a cosmic asymmetry? Here's where the plot thickens. The axis aligns suspiciously well with our solar system's orientation, raising eyebrows about potential measurement bias. Could our local motion through space somehow imprint this pattern? Yet meticulous checks show the anomaly persists even after accounting for the Milky Way's movement. Others propose more exotic explanations, a relic of pre-Big Bang physics, a collision with another universe, or even dark energy's hidden structure. If dark energy clumps or flows like a quantum fluid, it could stretch space-time unevenly, leaving behind this fingerprint. Then there's the dark flow, a separate but equally bizarre observation where galaxy clusters appear to stream toward a distant point beyond the observable universe, as if tugged by an unseen attractor. Could this motion and the axis of evil be connected? Some models suggest yes, that both anomalies stem from a primordial imbalance, a cosmic tilt frozen into the universe's fabric before dark energy took hold. Yet for all the theories, the axis of evil remains stubbornly unexplained. It's a crack in cosmology's foundation, a whisper that the universe might not play by the rules we've written for it. Future missions like the next-generation CMB-S4 experiment aim to scan the cosmic microwave background with even sharper eyes, hunting for clues in the faintest polarizations. Until then, the axis lingers a silent challenge to our understanding, a reminder that the cosmos might not just be expanding, but spinning its own mysteries in the dark. Galaxies don't form in isolation. They're woven into the universe's grand tapestry by gravity's relentless pull, clustering into filaments and nodes that span billions of light years. But dark energy isn't just a passive spectator in this cosmic dance. It's the disruptor, the force quietly unraveling gravity's work, stifling the growth of structures on the grandest scales. To understand how, we need to rewind the universe's clock to a time before dark energy took control, when gravity ruled unchallenged. Simulations of cosmic evolution paint a stark contrast. Run the universe's equations without dark energy, and you'll watch matter clump aggressively, galaxies merging into ever larger superclusters, drawn together by gravity's unopposed tug. But introduce dark energy and the story changes. Around 5 billion years ago, as dark energy's influence surpassed gravity's grip, the cosmic web's growth didn't just slow, it hit a wall. Vast filaments of gas and dark matter, once destined to fuel new galaxies, stretched thin instead, like taffy pulled too far. Galaxy clusters, which should have kept growing through collisions, found themselves frozen in time, their mergers thwarted by the accelerating expansion of space itself. The numbers are startling. In a dark energy-free universe, simulations predict galaxy clusters 10 times more massive than those we see today. The Virgo cluster, our local heavyweight, might have rivaled the monstrous Coma cluster in size. But dark energy pressed pause, leaving these structures permanently stunted. Even now, as you read this, galaxies at the edges of clusters are being yanked away by expanding space, their cosmic addresses shifting from urban centers to isolated outposts in the void. Yet dark energy's impact isn't uniform. Dive into supercomputer simulations and you'll spot a paradox. While it strangles growth on large scales, it barely touches the densest knots of the cosmic web. Within galaxy clusters, gravity's grip is still strong enough to resist dark energy's push for now. But over trillions of years, even these titanic structures will fray. The universe's future, as one astrophysicist put it, isn't fire or ice, but isolation islands of matter drifting apart in a sea of nothingness. This raises a haunting question. Did dark energy's rise come at the perfect time for life? If it had dominated earlier, galaxies might never have formed at all. Later, and we wouldn't witness its effects. The cosmic web's stunted growth isn't just a curiosity. It's a clue that the universe's expansion isn't just happening to us. It's part of the story that made us possible. What if dark energy isn't just hiding in the void between galaxies? What if it's lurking right here on Earth, cloaked by our planet's own density? This is the wild premise of chameleon fields, theories proposing that dark energy isn't a constant force but a shape-shifter, altering its strength based on its surroundings. In the emptiness of deep space, it could dominate, driving cosmic expansion. But in dense regions like our solar system, or even this room, it might shrink into near invisibility, evading detection like a cosmic chameleon blending into its environment. The math behind this is as elegant as it is strange. Chameleon fields are hypothetical scalar fields, cousins to the Higgs boson, that interact with matter in a way that depends on local density. Where matter is sparse, like the intergalactic void, the field's effects are strong, pushing space apart. But where matter crowds together planets, stars, even laboratory vacuum chambers, the field screens itself, dampening its influence to near zero. It's not just hiding, it's actively suppressing its own signature to avoid detection where gravity reigns. This screening effect could explain why we've never directly measured dark energy on Earth, despite its staggering cosmic influence. Imagine a force so finely tuned that it vanishes in your backyard but dictates the fate of galaxies. The chameleon doesn't break the rules, it bends them, tailoring its behavior to its surroundings. Scientists aren't just theorizing, they're hunting for these elusive fields in labs. One groundbreaking experiment used an ultra-high vacuum chamber with a floating aluminum sphere smaller than a grain of sand. By precisely measuring the sphere's movement as a nearby mass shifted, researchers sought traces of a possible fifth force, a whisper of the chameleon field's presence. So far, no luck, but the hunt has only tightened constraints, ruling out certain versions of the theory while leaving others tantalizingly plausible. Other tests exploit the field's predicted behavior in low-density environments. In space where matter thins out, chameleon fields should weaken their screening, potentially leaving faint signatures in the orbits of planets or the behavior of light. The European Space Agency's upcoming Ariel mission, designed to study exoplanet atmospheres, might inadvertently spot anomalies caused by these hidden forces. Critics argue that chameleon theories feel like a convenient patch, a way to explain dark energy's absence in our cosmic backyard. But supporters counter that they solve multiple puzzles at once. Why dark energy's effects are so finely tuned, why it's undetectable locally, and even why the universe's expansion kicked into high gear relatively recently. The chameleon isn't just hiding, it's rewriting the rules of the game, suggesting that dark energy's greatest trick might be its ability to disappear when we're looking too closely. The stakes, if chameleon fields are real, our entire understanding of fundamental forces could be upended. Gravity, electromagnetism, and the nuclear forces might have a hidden partner, one that spent 13.8 billion years playing the universe's greatest game of hide and seek. And the next experiment, the next lab test, might finally flush it into the open. Until then, the chameleon remains a ghost in the equations. A theory so bold it dares to suggest that dark energy isn't just out there. It's right here, watching us, waiting to be seen. String theorists have a name for ideas that seem mathematically elegant but might be fundamentally flawed. They call them the swampland. Unlike the landscape of viable theories, these are hypotheses that, no matter how beautiful their equations, could never describe our actual universe. And when it comes to dark energy, the swampland conjectures are tightening the noose, forcing physicists to question whether some of their favorite explanations, like quintessence, can survive at all. At the heart of this debate is a simple but brutal rule. In string theory, not all types of dark energy are allowed. One swampland conjecture suggests that if a theory involves a scalar field like quintessence with an overly gentle slope, meaning its energy changes too slowly across space, it's probably bogus. The math might work on paper, but the universe, it seems, has stricter taste. Think of it like building a sandcastle too close to the tide. The structure might hold for a moment, but eventually the waves of consistency will wash it away. For quintessence, this poses an existential threat. Many quintessence models rely on ultra-weakly interacting fields that barely change over billions of years, precisely the kind of shallow slope the swampland rules suspect. If these conjectures hold, then dynamic dark energy isn't just unlikely, it's mathematically forbidden, relegated to the realm of dead-end ideas. But here's where the plot twists. Some theorists are fighting back, tweaking quintessence to fit within the swampland's limits. Maybe the field isn't shallow but staggered, dropping in sharp steps rather than a smooth glide. Or perhaps it's trapped in a metastable state, like a ball balanced on a ridged hill, only rolling when jostled by cosmic events. These adaptations could let quintessence survive, not as a free-floating field, but as a prisoner of string theory's constraints. The stakes couldn't be higher. If the swampland conjectures are correct, then dark energy might not be a field at all but something far stranger, a topological defect in spacetime, a shadow of higher dimensions, or even an illusion born from our incomplete understanding of gravity. Every new observation of supernova or galaxy clustering isn't just measuring expansion, it's testing the boundaries of what's mathematically possible. So far, the verdict's unclear. Some versions of quintessence cling to life, while others sink into the swampland's mire. But one thing's certain, the universe isn't just expanding. It's forcing us to choose between our most elegant theories and the cold, hard rules of reality. And in that tension, dark energy's greatest mystery might not be what it is, but whether we're even asking the right questions. For decades, dark energy was considered a constant, a steady hum in the background of the cosmos. But what if its strength isn't fixed? What if it pulses, wanes, or even grows stronger as the universe ages? The quest to answer this has turned astronomers into cosmic detectives, scrutinizing two key clues: baryon acoustic oscillations and supernova. These aren't just esoteric terms, they're echoes from the universe's past, trails left behind as dark energy reshapes reality. Baryon acoustic oscillations sound complex, but they're essentially fossilized ripples from the early universe. Picture the cosmos as a primordial soup, hot and dense, where particles jostled like molecules in a pot of boiling water. When sound waves traveled through this plasma, they left faint imprints, regions where matter clumped slightly more or less densely. As the universe expanded, these imprints froze in place, leaving a telltale pattern in the distribution of galaxies. By measuring the spacing between these cosmic ripples at different epochs, scientists can track how dark energy's push has altered the universe's expansion rate over billions of years. The data reveals something curious. When comparing ancient baryon acoustic oscillations to those from more recent cosmic history, there's a whisper of deviation, a hint that dark energy's influence might not be perfectly uniform. It's as if the universe's acceleration has subtle fluctuations, like a car whose gas pedal isn't just pressed down but occasionally nudged harder or softer. Supernova add another layer to the mystery. These stellar explosions serve as cosmic lighthouses, their brightness revealing precise distances across the universe. By cataloging thousands of supernovas, some from when the universe was half its current age, astronomers have built a timeline of cosmic expansion. The surprise: The most distant supernova, whose light has traveled billions of years to reach us, sometimes appear slightly dimmer or brighter than expected if dark energy were truly constant. These anomalies are tiny, buried in margins of error, but they're persistent enough to raise eyebrows. Take the Dark Energy Survey's latest findings, for example. When researchers combined supernova data with Baryon acoustic oscillation measurements, they found a tantalizing mismatch. The universe's expansion rate around 5 billion years ago doesn't quite align with predictions based on today's dark energy strength. It's as if the cosmos hit a speed bump or a hidden accelerator during that epoch. Some models suggest dark energy's density might have dipped by a fraction during this period, like a flickering engine before revving up again. Critics argue these discrepancies could stem from measurement errors or unaccounted cosmic dust. But supporters of time-varying dark energy point to a pattern: multiple independent datasets from different telescopes and methods, all nudging toward the same unsettling possibility. The European Space Agency's Euclid mission, now mapping the cosmos in unprecedented detail, could settle the debate. Its precision measurements of galaxy clustering and weak gravitational lensing might finally catch dark energy in the act of changing its tune. If confirmed, the implications would rewrite cosmology. A dynamic dark energy could mean the universe's fate isn't a slow, cold fade, but something far more dramatic: a sudden collapse, a catastrophic rip, or even cyclical rebirth. For now, the evidence hangs in equilibrium, a delicate balance between possibility and uncertainty. But every new dataset brings us closer to answering the haunting question: is dark energy the universe's steady heartbeat, or is it a pulse that's slowly, or not so slowly, changing? At the centers of galaxies, supermassive black holes lurk like cosmic engines devouring stars, spewing jets of plasma, and shaping their surroundings with terrifying force. But what if these monsters aren't just passive products of dark energy's expansion? What if they're actively fueling it? This is the spine-chilling premise of the black hole dark energy feedback loop, a theory that twists our understanding of cosmic evolution into something far stranger. Picture an active galactic nucleus, the blazing heart of a galaxy where a supermassive black hole feasts on swirling gas. As matter spirals inward, it doesn't just vanish. Some gets blasted back into space in colossal jets, stretching hundreds of thousands of light years. These aren't just fireworks, they're cosmic plows, carving out cavities in the intergalactic medium and injecting energy into the void. Now imagine this process playing out across billions of galaxies over billions of years. The cumulative effect could be staggering enough to alter the very fabric of space itself, subtly boosting the expansion we attribute to dark energy. The math behind this idea is as elegant as it is radical. Black holes grow by swallowing matter, but general relativity predicts they also gain energy from the expansion of space, a phenomenon called cosmological coupling. In some models, this coupling means black holes effectively store vacuum energy, their masses increasing as the universe expands. When they feed, they release that stored energy back into space, creating a feedback loop where black holes don't just respond to dark energy, they amplify it. Observations add tantalizing weight to the theory. Surveys of active galactic nuclei show their jets are far more efficient at heating their surroundings than previously thought, preventing gas from cooling and forming new stars. On cosmic scales, this AGN feedback suppresses galaxy growth, leaving vast regions emptier, and emptiness, as we've seen, is precisely where dark energy thrives. The eerie implication: supermassive black holes might be cosmic sculptors, hollowing out the universe to make room for acceleration, yet the theory walks a tightrope. Critics point out that black hole jets, while powerful, operate on relatively small scales. Could they really influence something as vast as universal expansion? Supporters counter that the effect is cumulative, like trillions of ants moving a mountain one grain at a time. Each jet, each burst of energy contributes to a larger pattern we're only beginning to decipher. The stakes are cosmic. If this feedback loop exists, it means dark energy isn't just an immutable force, it's a dynamic process, shaped by the very structures it helps create. Black holes wouldn't just be monsters in the dark. They'd be architects of the universe's fate, their hunger and fury woven into the story of everything. And that changes the question from what is dark energy to something even more profound. Are we seeing the universe evolve or watching it engineer its own demise? What if dark energy isn't a force at all, but a cosmic illusion, a side effect of the universe hitting its information storage limit? This is the mind-bending premise of holographic dark energy, a theory that merges black hole physics with the accelerating cosmos. Picture the universe not as an endless void, but as a vast hologram where every event inside can be encoded on its outer boundary, like a 3D movie projected from a 2D surface. Strange as it sounds, this idea might hold the key to dark energy's deepest mystery. The holographic principle, born from studying black holes, suggests a radical trade-off. The maximum entropy, or information, inside any volume of space isn't proportional to its volume but to its surface area. Imagine stuffing a hard drive with data. Normally, you'd expect its capacity to grow with its size, but in a holographic universe, the real storage space lies on its outer shell. Pack too much information inside, and the system rebels not with an error message, but with a repulsive force we might call dark energy. Here's where it gets cosmic. In this framework, dark energy emerges from a tug of war between the universe's information budget and its expansion. As space grows, new volume outpaces the area of its boundary, creating an entropy deficit. Nature abhors this imbalance, responding with a pressure to restore equilibrium, a pressure that drives galaxies apart. Think of it like a balloon being inflated too fast. If the rubber can't stretch smoothly, it develops tension. Dark energy, in this view, is the universe's way of reconciling its inner complexity with its outer limits. The numbers are eerily precise. Calculations based on the holographic principle predict a dark energy density within spitting distance of observed values, unlike the catastrophic mismatch of quantum vacuum energy predictions. Even more compelling, this model naturally explains why dark energy became dominant relatively recently. In the early universe's dense, compact state, information bounds weren't threatened. But as space ballooned, crossing a critical threshold, the holographic overhead kicked in, like a cosmic switch flipping to acceleration mode. Critics argue the theory is more metaphor than mechanism, a clever analogy without a concrete quantum gravity foundation. Yet supporters point to the AD/CFT correspondence, a rigorously tested holographic model in string theory, where a higher dimensional universe's physics is perfectly mirrored on its lower dimensional boundary. If our reality operates similarly, dark energy might be the shadow of a deeper mathematical truth, that the universe isn't just expanding, it's encoding itself at the edges, one cosmic pixel at a time. Future telescopes could test the idea by hunting for subtle deviations in dark energy's behavior, predicted by holographic models, variations that a static cosmological constant can't explain. Until then, the theory offers something profound, a vision of the cosmos where the acceleration we measure isn't just a force but a message, a sign that reality's true nature might be written not in the stars but on the surface of the dark. The universe hums with a hidden rhythm, a faint echo from its earliest moments that still ripples through space today. These are Baryon acoustic oscillations, sound waves frozen in time, imprinting the cosmos with a pattern so precise it serves as a cosmic ruler for measuring dark energy's invisible hand. Picture the newborn universe, a seething plasma of particles and light, where pressure waves surged outward like ripples in a pond. As the cosmos expanded and cooled, these waves froze in place, leaving behind a telltale signature. galaxies slightly more likely to form at specific distances from one another, like beads strung along an invisible thread. Now fast forward 13.8 billion years. Surveys like the Sloan Digital Sky Survey map millions of galaxies in 3 dimensions, revealing this ancient fingerprint. The spacing between galaxy clusters isn't random, it's staggered at intervals of about 500 million light-years, a relic of those primordial sound waves. By measuring these intervals across different epochs, astronomers can track how dark energy has stretched the fabric of space over time. It's like finding a stretched-out tape measure buried in the cosmos. The further apart the marks, the harder dark energy has been pulling. The data tells a startling story. When scientists compare baryon acoustic oscillations from the distant past to those in the more recent universe, they see a clear shift. Earlier in cosmic history, gravity's grip kept expansion in check, and the ruler stayed relatively consistent. But as dark energy took dominance, the intervals began to stretch faster, like a rubber band accelerating under an unseen force. These measurements don't just confirm dark energy's existence, they reveal its timing, its strength, and even hint at whether its effects have changed over billions of years. What makes baryon acoustic oscillations so powerful is their independence from other methods. Unlike supernova, which rely on the brightness of dying stars, or cosmic microwave background radiation, which captures a single moment in time, these oscillations provide a continuous record, a cosmic timeline etched into the distribution of galaxies. Surveys like DECay, the Dark Energy Spectroscopic Instrument, are now mapping tens of millions of galaxies with unprecedented precision, turning this subtle signal into a high-definition movie of dark energy's influence. Yet the oscillations harbor mysteries of their own. Some models suggest slight deviations from the expected pattern, tiny kinks that could mean dark energy isn't constant but evolving. Others wonder if the voids between galaxy clusters, those vast cosmic deserts, might be amplifying the signal in ways we don't yet understand. Every new data point sharpens the picture, but also deepens the questions. In the end, baryon acoustic oscillations are more than just a tool. They're a bridge across time, connecting the universe's fiery birth to its accelerating present. And as telescopes peer deeper into the cosmic web, they're not just measuring distances, they're listening to the echoes of a younger cosmos, decoding the whispers of a force that's shaping everything, everywhere, all at once. Why does dark energy have the exact value it does? Not 10 times stronger, not 1,000,000 times weaker, but precisely the minuscule fraction that allows galaxies, stars, and life to exist? One controversial answer lies beyond our universe. Picture an infinite multiverse, a sea of bubble universes, each with different physical constants. In most, dark energy's strength would be too weak to matter, or so overwhelming it tears space-time apart before galaxies can form. But in a rare subset like ours, the numbers align just right. This is the anthropic principle in action. Dark energy's value isn't fine-tuned by design, but by the simple fact that we're here to observe it. The math behind this idea is staggering. Quantum field theory predicts dark energy's density should be around 10 to the power of 120 times larger than observed, a number so vast it dwarfs every particle in the universe. Yet somehow it's dialed down to 1 part in 10 to the power of 120. The odds of this happening by chance are like flipping a coin and getting heads 10,000 times in a row. But in a multiverse with infinite tries, even the most improbable outcomes become inevitable somewhere. Critics call this a cop-out, a way to dodge the search for deeper physics. If every possible universe exists, they argue, science loses its predictive power. Why bother explaining dark energy's value if anything goes in some alternate reality? Supporters counter that the multiverse isn't just philosophical hand-waving. String theory, for instance, naturally generates a landscape of possible universes, each with different vacuum energies. Our universe's dark energy might simply be the luck of the draw, one configuration in an unfathomably vast cosmic lottery. Then there's the eerie alternative. What if dark energy isn't constant across the multiverse but evolves? Some models suggest baby universes inherit traits from their parent-like genetic mutations, with dark energy's strength subtly shifting each time. In this scenario, life-friendly universes aren't random accidents but products of cosmic natural selection, where only the Goldilocks zones survive long enough to spawn observers. The debate cuts to the heart of cosmology. Is our universe a one-off masterpiece or just one page in an endless library of possibilities? Future telescopes might find clues in the cosmic microwave background, anomalies that hint at collisions with other bubble universes. Until then, dark energy's uncanny balance remains either the universe's greatest coincidence or its quietest confession that we're not alone, and that changes everything. Not just what we are, but where and how many times we might be. Neutrinos are cosmic ghosts, particles so elusive they can pass through light years of lead without a trace. But what if these shadowy particles hold a secret connection to dark energy? Deep underground, in laboratories shielded from cosmic rays, physicists have spotted strange anomalies in neutrino behavior that hint at something beyond our current understanding. These aren't just measurement glitches, they could be the first whispers of a hidden particle, the sterile neutrino, a theoretical variant that doesn't interact with matter at all except perhaps through gravity. And if sterile neutrinos exist, they might be threading the needle between the quantum world and the accelerating cosmos. Take the LSD and mini Buoni experiments, for example. Designed to study neutrino oscillations, the phenomenon where neutrinos switch between different flavors as they travel, these detectors recorded more oscillations than the standard model predicts. The discrepancy is small but persistent, like a clock that consistently runs a few seconds fast. One explanation, a fourth neutrino, one that's sterile because it ignores the weak nuclear force, slipping through detectors like a burglar avoiding motion sensors. If real, these particles would be absurdly abundant, outnumbering regular neutrinos by orders of magnitude. And here's where dark energy enters the picture. Sterile neutrinos could be more than just oddball particles. Some theories suggest they interact with whatever field drives dark energy, acting as a cosmic middleman between the quantum vacuum and the large-scale structure of the universe. Imagine them as invisible messengers, translating the seething energy of empty space into the repulsive force pushing galaxies apart. It's a wild idea, but the math is tantalizing. If sterile neutrinos have just the right mass, somewhere around 1 electron volt, their gravitational influence could mimic dark energy's effects without requiring new physics. Then there's the Casimir effect, where quantum fluctuations create measurable forces between closely spaced metal plates. If sterile neutrinos contribute to these fluctuations, they might subtly alter the vacuum energy in ways that telescope observations could one day detect. Critics argue the evidence is still thin. Sterile neutrinos remain hypothetical, and alternative explanations for oscillation anomalies exist. But supporters point to upcoming experiments like the Deep Underground Neutrino experiment, which could finally catch these phantoms in action. The stakes: if sterile neutrinos bridge dark energy and particle physics, it would rewrite the rules of both. No longer would dark energy be a disembodied force. It would have a face, or at least a shadow, one that's been flitting through our detectors all along, unnoticed. The universe's greatest mystery might not be hiding in the void after all, but in the faint trails of particles we're only now learning to see. The next chapter in our quest to unravel dark energy's secrets won't be written in chalkboard equations. It'll be etched in light, captured by a new generation of telescopes designed to probe the cosmos with unprecedented precision. Leading the charge are two cosmic detectives, the European Space Agency's Euclid and NASA's Nancy Grace Roman Space Telescope. these aren't just upgrades, they're paradigm-shifting observatories armed with instruments fine-tuned to stalk dark energy's elusive footprints across the universe. Euclid, launched in 2023, is essentially a cosmic cartographer. Its mission: to map the three-dimensional distribution of billions of galaxies across 10 billion light-years, tracing the invisible scaffolding of dark matter that shapes their positions. But here's the twist: it's doing this with two groundbreaking tools. The visible imager captures razor-sharp images of galaxies, while the near-infrared spectrometer measures their redshifts, revealing how fast they're receding from us. Combined, these instruments let Euclid reconstruct the universe's expansion history with staggering detail, searching for minute variations that could betray dark energy's true nature. Then there's the Roman Space Telescope, set to launch by 2027. Imagine Hubble's clarity coupled with a field of view 100 times wider, a game-changer for surveying vast swaths of sky quickly. Roman's secret weapon is its ability to measure weak gravitational lensing, the subtle warping of light from distant galaxies as it passes through dark matter's gravitational field. By tracking how this lensing evolves over cosmic time, Roman could detect whether dark energy's strength has changed, testing theories like quintessence against the static cosmological constant. But these telescopes aren't working alone. Synergy is key. Euclid's wide-field surveys will identify intriguing targets for Roman's deeper dives, while Roman's high-resolution data can calibrate Euclid's measurements. Together, they'll cross-examine the universe's acceleration like never before, hunting for discrepancies in supernova brightness, baryon acoustic oscillations, and galaxy clustering that might reveal cracks in our current models. The stakes: these instruments could finally answer whether dark energy is a constant vacuum property or something dynamic, a shift that would rewrite textbooks. If their data tilts toward evolving dark energy, it might validate string theories, swampland conjectures, or hint at undiscovered particles. If it confirms a static cosmological constant, the mystery deepens. Why this specific infinitesimal value? Beyond them, next-gen ground-based observatories like the Vera C. Rubin Observatory will scan the entire visible sky every few nights, catching transient events like supernova in real time. Meanwhile, the Dark Energy Spectroscopic Instrument is already cataloging millions of galaxies, their precise distances acting as mile markers in the universe's expansion. What makes this era unique isn't just the technology, it's the convergence. For the first time, we're not peering at dark energy through a keyhole. We're throwing open the doors, armed with tools that can triangulate its influence across time, space, and even dimensions. The answers won't come easy, but the hunt is on. And somewhere in the flood of data these telescopes will beam back, dark energy's truth might finally flicker into view. Einstein's general relativity is a masterpiece of mathematical elegance, describing gravity as the curvature of space-time with breathtaking precision. But when you push its equations to their limits, especially in the presence of dark energy, it starts scribbling strange and terrifying possibilities in the margins. One of the most unsettling, phantom fields, a class of solutions where the energy density turns negative, warping space-time in ways that defy intuition. Picture gravity not as a pull, but as a push so extreme it makes galaxies accelerate apart faster than light, shredding the cosmic web atom by atom. These phantom fields emerge from a simple but radical tweak to Einstein's equations. Let the pressure of dark energy be more negative than its energy density. In normal physics, this violates what's called the null energy condition, a rule that keeps spacetime stable. Break it, and you unlock scenarios where gravity becomes repulsive on steroids. The equations describe spacetime not just expanding, but unzipping, stretching so violently that even atoms and nuclei can't hold together. It's the mathematical backbone of the Big Rip, but the real shock isn't just the apocalypse it predicts. It's that these solutions exist at all, buried in the same math that describes black holes and planetary orbits. Visualizing this requires bending your mind like space-time itself. Imagine a rubber sheet representing the universe. Normal matter dimples it inward, creating gravity's pull. Dark energy, as we usually think of it, stretches the sheet taut. But a phantom field, it's like hooking the sheet to a runaway winch, yanking it so hard that the fabric strains, thins, and eventually tears. The equations even permit wormholes, shortcuts through space-time, but fueled by negative energy. They'd collapse instantly unless phantom fields stabilize them. The kicker, some of these bizarre solutions might not just be mathematical curiosities. Quantum fluctuations near black holes or in the early universe could momentarily spawn phantom-like conditions, like rogue waves in a cosmic ocean. And if certain string theory conjectures are correct, our universe's late-time acceleration might require these extreme states, threading the needle between existence and oblivion. Yet the math has its skeptics. Many physicists argue phantom fields are artifacts, unnatural solutions that would destabilize the quantum vacuum, spawning particle pairs from nothingness until spacetime erupts in chaos. Others counter that nature isn't obliged to obey our intuitions. After all, dark energy itself was once deemed impossible until telescopes proved otherwise. Whether phantom fields are real or relics of untamed equations, they force a humbling realization. General relativity, our best theory of gravity, contains shadows of phenomena we're only beginning to glimpse. And somewhere in those shadows, dark energy's true face might be hiding not just as a number, but as a shape, a texture, a scream written in the language of space-time itself. Could everything we think we know about dark energy be wrong? What if the universe isn't accelerating at all, and the evidence we've built our theories on is nothing more than a cosmic sleight of hand? This isn't just skepticism, it's a radical re-examination of the data, one that suggests dark energy might not be a force but a flaw in how we interpret the cosmos. Take those distant supernovae, the very same ones whose dimmer-than-expected glow first revealed accelerating expansion. New studies suggest their faintness might not stem from the universe speeding up, but from something far simpler: dust. Intergalactic space isn't perfectly empty. It's strewn with microscopic particles that could subtly dim starlight over billions of light years, mimicking the signature of dark energy without requiring its existence. Early surveys might have underestimated this effect, like mistaking a dirty telescope lens for a fading star. Then there's the way we model the universe itself. Cosmologists rely on the cosmological principle, the assumption that space is uniform on large scales, no special places, no preferred directions. But what if that's not entirely true? The axis of evil, those bizarrely aligned fluctuations in the cosmic microwave background, hints at a universe that's lumpier and less predictable than we thought. If matter isn't evenly distributed, our measurements of expansion could be skewed, like trying to gauge the ocean's depth while ignoring its waves. Even the cosmic voids, those billion light-year bubbles of near-nothingness, might be playing tricks on us. Light passing through these emptier regions gains energy differently than in dense galaxy clusters, an effect that could masquerade as accelerated expansion when viewed from afar. It's like hearing an echo in a canyon and mistaking it for the sound of the wind speeding up. The boldest critics go further, arguing that general relativity itself might break down on cosmic scales. Modified gravity theories, like grown-up cousin TVS, attempt to rewrite Einstein's equations to explain galaxy rotations and cosmic acceleration without dark energy. These theories aren't fringe, they're testable, and some even match existing data better than the standard model in certain regimes. Yet for all these alternatives, dark energy remains the reigning explanation because it fits so much data so well. But science thrives on doubt, and every anomaly, every cold spot, every skewed measurement is a thread that, if pulled, could unravel our understanding entirely. Perhaps dark energy is real, perhaps it's the universe's greatest illusion, or perhaps the truth is something stranger still, waiting in the shadows of our next observation, our next calculation, our next leap into the unknown. The mystery isn't just about dark energy, it's about how well we truly know the cosmos at all. The vacuum catastrophe isn't just a scientific problem, it's a screaming contradiction at the heart of modern physics. Quantum field theory tells us empty space should be a boiling cauldron of energy, with particles and antiparticles constantly flickering in and out of existence. This quantum foam isn't hypothetical. We've measured its effects in lab experiments like the Casimir force, where metal plates in a vacuum inexplicably push together because of these fleeting fluctuations. But here's the crisis. When physicists calculate how much energy this quantum frenzy should contribute to the cosmos, they hit a number so absurd it defies comprehension, 10 to the power of 120 times larger than what dark energy's observed strength actually is. That's a 1 followed by 120 zeros, a discrepancy so vast it's like predicting an ocean and finding only a single drop. To understand why this happens, you need to grasp renormalization, a mathematical trick physicists use to tame infinity. In quantum field theory, when you sum up all possible particle interactions, the equations often spit out nonsensical infinite values. Renormalization steps in by effectively subtracting these infinities, leaving behind finite, measurable quantities. It's like balancing a checkbook where some entries are scribbled as infinity dollars, but by clever accounting, you end up with a real number you can work with. This works brilliantly for predicting particle masses and charges, but when applied to vacuum energy, the process fails catastrophically. The core issue lies in UV cutoffs, the energy scales at which we stop counting contributions to the vacuum. In theory, quantum fluctuations occur at all possible energies, from the mundane to the Planck scale, where gravity becomes as strong as the other forces. But summing them up without a cutoff gives that insane 10 to the 120 result. To fix this, physicists impose an artificial upper limit, essentially saying, we'll ignore any fluctuations above this energy. The problem, even if you set the cutoff just above the highest energies we've probed in particle colliders, the predicted vacuum energy is still billions of times larger than observed. Some argue the solution lies in supersymmetry, a theorized symmetry between particles and their superpartners that could cancel out vacuum energy contributions. But supersymmetry hasn't shown up in experiments, leaving the mystery wide open. Others propose that gravity somehow ignores vacuum energy, a loophole in Einstein's equations we've yet to uncover. Then there's the radical idea that our universe is holographic, that the true degrees of freedom aren't in the volume of space but on its boundary, making the vacuum energy we perceive a shadow of deeper physics. The vacuum catastrophe isn't just an academic curiosity. It's a direct challenge to our understanding of reality, exposing a rift between quantum mechanics and general relativity so deep that resolving it might require rewriting the laws of physics themselves. Every attempt to bridge this gap from string theory to emergent gravity has stumbled over this same colossal mismatch. Until we crack it, dark energy remains not just a mystery, but a cosmic anomaly screaming that somewhere, somehow, we've gone profoundly wrong. Hidden between the blinding glow of galaxy clusters lie the universe's most enigmatic highways, dark filaments, rivers of invisible energy stretching millions of light years, weaving the cosmic web into a single connected structure. These aren't empty voids, they're dynamic bridges thrumming with dark energy's push and pull, and for the first time we're beginning to map them not by the light they emit, but by the way they bend reality itself. The Hubble Space Telescope's keen eye has captured something extraordinary, ghostly distortions in the light of distant galaxies, warped as if viewed through a funhouse mirror. This is gravitational lensing in action, the bending of light around massive objects, a phenomenon Einstein himself predicted, But here's the twist. The distortions don't always align with visible matter. Instead, they trace invisible filaments, colossal strands of dark energy and dark matter binding galaxy clusters together like threads in a spider's web. When Hubble's lensing maps overlay traditional galaxy surveys, the mismatch is undeniable. There's an unseen architecture at work, and it's far more intricate than we ever imagined. Picture the universe as a vast network of cities' galaxy clusters linked by highways, dark filaments. These highways aren't empty. They're dense with dark matter and suffused with dark energy's repulsive force, creating a delicate balance. Gravity tries to pull everything together while dark energy stretches the space between. The result, filaments that aren't static. They vibrate, funneling galaxies toward clusters while simultaneously being stretched apart by cosmic expansion. It's a cosmic tug of war where the rope itself is alive, twisting and flexing under conflicting forces. One of the most startling discoveries comes from the Clash survey, where Hubble peered through a galaxy cluster called MAX J0717. The lensing patterns revealed a filament stretching over 50 million light-years. Its gravity so pronounced it magnified the light of galaxies far behind it. But here's the kicker: the filament's shape didn't match simulations. It was lumpier, more dynamic, as if dark energy had stirred it like cream in coffee. This isn't just a bridge, it's a living structure, evolving in ways our models struggle to predict. The implications ripple outward. If filaments are active participants in cosmic evolution, not just passive scaffolding, they could solve lingering mysteries. Take the missing baryon problem. About a third of the universe's normal matter isn't where we expect it. These dark bridges might hide it, their gravity trapping hot gas in a diffuse, invisible fog. Or consider galaxy spin. Some rotate faster than visible mass explains. Could dark filaments be whipping them up like cosmic conductors, their unseen momentum transferring energy across the web? Future telescopes like NASA's Nancy Grace Roman Space Telescope aim to map these filaments in 3D, using lensing to reconstruct their shapes like celestial MRI scans. Each new map peels back another layer of the cosmic web, revealing not just where dark energy lies, but how it moves, how it shapes the universe's grand design. The bridges are there, hidden in plain sight, waiting for us to cross them, to follow their paths into the dark. Time crystals sound like science fiction, but they're real, and they might hold the key to understanding dark energy's most puzzling behaviors. Unlike ordinary crystals, which arrange atoms in repeating patterns in space, time crystals repeat their structure in time, flipping between states indefinitely without energy input. It's as if you tapped a pendulum once and it kept swinging forever, defying the laws of thermodynamics. In labs, researchers have created these exotic structures using chains of ions or diamond defects, coaxing them into a bizarre quantum dance where entropy doesn't increase and motion never winds down. Now imagine scaling this up to cosmic proportions. Could the universe itself harbor time crystal-like behavior with dark energy as its rhythm? Footage from a Berkeley lab shows a time crystal in action, laser's pulse, and a ring of ytterbium atoms responds by oscillating at a fraction of the laser's frequency, locked in a perpetual loop. This isn't just a curiosity, it's a system that spontaneously breaks time symmetry, meaning it doesn't play by the usual rules of cause and effect. Dark energy, too, seems to break cosmic symmetry, driving expansion that ignores gravity's pull. The parallel is striking. Both phenomena defy equilibrium, both exist in a state of continuous, energy-free change. Could dark energy be the universe's version of a time crystal, a structure that repeats not in space but in the fabric of space-time itself? The math whispers tantalizing possibilities. Some theories suggest time crystals could emerge in extreme environments like the chaotic soup of particles near a black hole's event horizon or the seething quantum foam of the early universe. In these realms, dark energy's repulsive push might have crystallized into a dynamic pattern, a cosmic heartbeat driving acceleration. Even stranger, time crystals exhibit non-local behavior, where changes in one part instantly influence another, eerily reminiscent of dark energy's uniform influence across vast distances. Yet the leap from lab bench to cosmos is vast. Time crystals today are fragile, tiny, and demand near absolute zero temperatures. Scaling them to universal proportions would require rewriting physics as we know it, but that's exactly what dark energy has already forced us to consider. Whether a dead end or a breakthrough, the experiment footage alone is a revelation, a glimpse of a world where time itself can be ordered, structured, and perhaps even harnessed. If dark energy shares these properties, the universe isn't just expanding, it's ticking, cycling, echoing in ways we're only beginning to hear. The real magic lies in what we haven't seen yet. Future experiments could probe whether time crystals emit gravitational waves or interact with vacuum energy, hunting for echoes of dark energy's signature. Until then, these lab-grown oddities offer something priceless. A new lens to stare into the abyss where the answers might not be particles or forces, but patterns written not just in space but in time itself. From the ghostly pull of phantom energy to the cosmic scaffolding of dark filaments, we've journeyed through 25 mysteries that make dark energy the greatest puzzle of our universe. It's the force rewriting cosmic history, not just as a footnote but as the author of reality itself. Whether it's black holes leaking gravity into higher dimensions, time crystals echoing in the quantum void, or the chilling possibility that we're misreading expansion entirely, each revelation peels back another layer of the unknown. Dark energy isn't just stretching space, it's stretching our understanding, bending the rules of physics until they crack under the weight of new questions. Think about it, every galaxy, every atom, every moment of existence is caught in a tug of war between gravity's embrace and dark energy's relentless push. The cosmic web isn't static, it's a living, breathing network where voids grow hungrier, filaments tremble with hidden energy, and black holes might be quietly fueling the acceleration. Even time itself could be part of this dance, with the universe ticking like a colossal time crystal, cycling through states we've yet to comprehend. What makes these mysteries so electrifying isn't just their complexity, it's the way they force us to rethink everything, the standard model of physics. Incomplete, Einstein's gravity potentially up for revision, the fate of reality hanging in the balance between a cold, empty fade and a violent rip at the seams. And the wildest part, we're not just observers, we're participants living in the narrow sliver of cosmic time when these questions can even be asked. So here's the real challenge. Which mystery hooked you? Was it the phantom fields lurking in Einstein's equations, the cosmic voids masquerading as acceleration, or the chilling "why now" coincidence that hints at a universe fine-tuned for curiosity? Drop your thoughts below. Let's geek out over the enigmas that keep astronomers awake at night. And if you're craving more deep dives into the cosmos, hit subscribe. The universe has plenty more secrets to spill, and we're just getting started.